Hi everyone, in this video we're going to be looking at example 1 on the Module 4 lecture guide. So in example 1 we're looking at 3 different people, person A, person B, and person C, and they're each going to play rock, paper, scissors. What we want to do is test each person to find whether the long run proportion of times the person picks scissors is less than a third. So for some reason do they not seem to be throwing a third as much as we would think if they're just picking randomly. So in A, it asks us to identify the null and alternative hypotheses. So for each person, so that's what I mean here with these symbols. For both A, for B, and C, the hypotheses read pi is 0.33, because that's 1/3. Person A throws scissors 33% of the time in the long run. The alternative, person A throws scissors less than 33%. Because in the problem it tells us less than. And so you can replace A with B or C in here to get the hypotheses for each person. B says identify the sample statistic for each person with the correct symbol. So for person A, we had 18 out of 60. Person B, 180 out of 600. Person C, 15 out of 60. And the percentages there are right here, 30, 30, and 25. Okay, so for C it says, tell me what to put in the applet, give me the screenshot of the applet, and then we'll answer some questions off of it. So that's what we did here. So for each person, our null hypothesis was equal to 33%. So that's why this box is the same, 0.33. Then the sample sizes were different, right? 60 for A, 600 for B, 60 for C. That's the second box across. And then we're just going to do 1,000 repetitions for the simulation here. Okay, so to find the p-value, remember you have to put your statistic in the box here. So I did that, 18 for person A, 180 for person B, and then 15 for person C. And then you'll also notice I did the less than symbol. Why? Go back to your null or your alternative hypothesis. We're interested learning if these people are throwing less than a third, less than random, so we put the less than symbol. What will that produce? That'll produce these 3, let me zoom in a little bit for you, these 3 distributions, right? A, B, and C. And then you can see the p-value. Again, I'm finding 18 in this one. I'm coloring in all the dots at 18 or more extreme, and we're using less than because of the alternative, so we go left. And what the computer's saying is that 40% of those dots are colored in. So 40% of the simulations the computer did ended up being as extreme or more extreme than our actual statistic, our actual results from person A. Person B, on the other hand, only 4.7% of the dots are colored in. And person C, 11.4% of the dots are colored in. Again, though, I'm finding it going left. Finding, go left. Finding, go left. So those are our p-values. 0.4, 0.047, 0.114. So in D, it asked me to just answer some questions about this. Okay, so person A, we got a p-value of 0.4. Just read it right off. So now we have to calculate the standardized statistic. And remember the formula. Stat minus mean of the null, or the center of your picture, over standard deviation of your picture. Okay, so we had 18 successes in our statistic. Person A chose scissors 18 times. We expected them to do it 20 times, because 20 out of 60 is 1/3, but I'll show you where to get that from the picture. And then this is our standard deviation. So I forgot to press the button on this picture, so I had to create a new one, so just so to show you where I got everything from. So this is a different chance model, very similar, right? Because they should be very similar, but slightly different numbers. So again, if you're not sure where to look, your mean, so that's 20 rounded, so this right here goes here, and then your standard deviation, again, we're a little bit off, that's fine, would go here. So you plug that in and you get negative 0.55. So what are these telling us? Well, if we assume person A throws scissors 33% of the time in the long run, how did I get that? Why is that our assumption? Well, we're assuming it to make this picture, and I just copy and pasted from up here. Because remember, we're assuming the null hypothesis, so I just copy and pasted down here. If we assume the null hypothesis, that they're really throwing 33% of the time scissors, then the probability of getting a sample like ours or more extreme, remember to us that meant go left here, is 40%, because that's the definition of the p-value. It's the probability of getting our statistic or more extreme, assuming that the null is true. And how did we put that into our process? That's how we created the picture. So the rest are very similar to this. We put the p-value down, we calculate the standardized statistic, okay? Then what do? Well, we throw in our null hypothesis. We throw in like a sample like ours or more extreme, and then we turn this into a percentage. And then our conclusion in this case, so I'll go back to the conclusion here. The conclusion in this case is, well, this p-value is less than 0.5. So this is less, smaller than 0.05. Okay, so if your p-value is less than 0.05, we are going to say we have evidence for the alternative. But that's not what I wrote here, right? Well, it is. The alternative is that person B throws less than 33%. So what did I do? Scroll back up. I just copied this, our alternative, and pasted it in here. We have evidence that, paste the alternative. So just to go back up to this one, because I missed it, a p-value of 0.4 is very big. So in that case, if you're looking back at your little number line, we're going to say the null is plausible. So it is plausible that, and then copy and paste the null in here. Person A throws scissors 33% of the time. Okay. And then the last one is, again, very similar. Your p-value, calculate your standardized statistic, copy and paste your null hypothesis. This sentence very similar, and 0.114 is bigger than 0.05, so we're going to say the null is plausible. So for E, based on our conclusions, who had the strongest evidence? Person B had the strongest evidence. They're the only one that we said we support the alternative, so that's one clue. The other one is just look at the p-value. 0.11, 0.04, 0.4. This is the smallest, so that means the strongest. Okay. A and B both had the same statistic, 30%. One was 18 out of 60, one was 180 out of 600. But person B had a smaller p-value. How come? Well, as we saw above, if you increase the sample size, but don't change anything else, then you're going to have stronger evidence. So a larger sample size with nothing else changed, that's important, means stronger evidence. Okay, A and C had the same sample size, but C had a smaller p-value. How come? Well, even though they had the same sample size, they both played rock, paper, scissors 60 times. Person C had a more extreme statistic, right? It was further in the tail. So let's go back up, right? 15 is further in the tail than 18. 18 is pretty close to the middle, but 15 is a little further out. More extreme, more evidence. Okay, H. We used a one-sided test for each of these hypotheses. What would it mean to switch to two-sided? Well, if we switch to two-sided, as we mentioned above when we first talked about this, switching to two-sided means that we're gonna lose some of our strength of evidence. But we could just start with writing out our alternative. Instead of less than 33%, it would become person, whichever one, A, B, or C, does not throw 33%. So we are now trying to find evidence for both they throw less than or they throw greater than. Could be either, right? So then remember what we said. When you do that, when you switch from one thing you're trying to find evidence for to now two things, that same amount of evidence, your statistic, does not go as far. So what does that do? That increases the p-value, which means you have less evidence. So two-sided, less evidence. That's what you have to remember. So that's it. These are the three things that we can do, right? So we can talk about our statistic being further into the tail, that's going to change our strength of evidence and then our p-value as well, right? We can change the sample size. That'll also have an impact. Increase your sample size, increase your strength of evidence. And then the last thing we could do is we could switch from a one-sided test to a two-sided test, or vice versa. But if you go to two-sided, you will have weaker evidence, larger p-value. So remember, the bigger the p-value, the weaker the evidence.